Okay, today we are going to start a very new topic, that is wave optics. Okay, so let us wait for other students to join, then we'll soon start the class. So here I take the black pen. Let us see what is happening on the YouTube. Just wait. Okay, we'll start the new chapter, wave optics. So you can write the heading. I'm showing you the contents list here. So write this as the front page of the chapter. Okay. See, first, what we are going to study here. First, what we'll be studying here is this. That is, we'll go through this Huygens or Huygens theory. Okay, we'll go through the Huygens theory. Somewhere it's been pronounced as Huygens. Somewhere it's been sorry. Somewhere it's been pronounced as Huygens theory. Okay, this is the first topic here. Second, we'll be studying what? Interference. Okay, so second, we'll be studying interference. Then at the third, we'll go through diffraction or diffraction. Fourth is this, that is polarization. Okay, so I'm starting it. So this is somewhat about the history of this chapter. Okay, just wait, students. Note it down, the history points. Then we'll proceed towards the next. Okay, for a while you may feel this is like mute. Okay. So see what happened in 1637. First, just let us talk about this. These are very interesting points. Okay. So whenever we are starting a chapter, if we know about the history, it makes us feel good. So this is what history. So there was one scientist, physicist, whose name was what? Whose name was Descartes. Okay. So what this person did, he founded the corpuscular model of light. Okay. He founded this model which is known as corpuscular. So what this model says, what this model explains, this model explains like this, that light consists of corpuscles of energy, or these are, yeah, so when I've joined, very good, very good. Who is this? Okay, sir, you are. Hello.
Yeah, Abhishek.
In
Yeah,
that he
yeah.
analyzed why which college they have gone, वगैरह. उसमें three will not get this for sure.
So your voice is not audible, sir. Okay, hold on, students. This. So first we'll go through the Huygens theory, write this in your notes. And then interference, I have already told. Then diffraction, then polarization. Okay. See, this is about the history. There was an year which is 1637 in the past. Okay. There was a physicist, Descartes. He developed a theory which was named as corpuscular model of light. According to this theory, what happens is this: these are energy particles. He told like this: light is made up of corpuscles of energy, which are energy particles. Okay. And if by using this, he derived the Snell's law also. Also, we have studied this thing, student, that in the previous chapter, that is ray optics, we studied that Snell's law was what? What was the mathematical interpretation of the Snell's law? It was like this: n1 sine I equals to n2 sine r, where n1 is what? N1 is the refractive index of the first medium. Let us say the medium in which the ray is like incident ray. Okay, so it's that first medium. N2 is the refractive index in which the refraction is like being continued. Refracted ray is there. Okay, so this is the second. By using this, he explained the reflection process also. This is what kind of process? This is reflection process. Okay. And then he also explained the next, that is refraction process. What kind of process? Refraction process. I hope I'm audible, no? And this is refraction process. Okay, let us little bit do revision of what? Little bit do revision of what? Reflection and refraction process. See what happens. Initially, we have studied this thing in the ray optics, that refraction is what? When the ray is incident straight, okay? When a ray is incident like this straight, this is incident ray, it gets reflected like this. This is angle of incidence, this is angle of reflection. Okay, this all we know already. Anna. And when we talk about this refraction process, what happens in this? That this is the angle of incidence in a rarer medium. This is the angle of refraction in a denser medium. And we can see here the angle of refraction, the angle of incidence is basically greater than the angle of refraction. What's the reason is? Because we have studied this thing, that when the light travels from a rarer medium to a denser medium, what happens? When the light travels from a rarer medium to a denser medium, it bends towards the normal. Okay. Yes. So, I mean, these things we have already studied in ray optics. But was the problem is this? I mean, we'll not say the problem. The proof is not there. Okay. So in the wave optics, we'll see that by treating the light ray as a wave, we can show many of the derivations which are actually not available. I mean, the direct formulas we have seen. Okay. So this was in 1637. This was Descartes, sent by Descartes. Okay. Write in your notes. And reply in the chat box if you want me to put the next slide fast. Yeah, Jane V. Rangareddy students, welcome to today's class. Please reply in the chat box if you want me to, like, Click on the next slide. You want me to proceed towards the next slide? Reply, students. I'm waiting for your reply. Yes or no? I'm waiting for your reply, students. Okay, we'll proceed. I'm closing this video. Maybe some network issue is there. So let us move towards the next now. So this was about 1637. This is the story of 1637. Starts with Descartes, and let's see when it ends. So this story ends at 1672. So this many years of time between. Okay. So then comes a new one. Isaac Newton is a very famous. You know this thing. He's known as the father of classical mechanics. Okay. He's known as the father of classical mechanics. Father of classical mechanics. Okay. And he also worked on the corpuscular model of light, which says like this, that light is made up of particles of energy or corpuscles of energy. Corpuscles of energy or the particles of energy are, students, the same thing here. Okay. These are corpuscles of energy. This theory was developed by Isaac Newton. Also, he have published a paper. In that paper, he has written his theory, and the name of the paper was Optics, or a treatise of the reflections, refractions, inflections, and colors of the light. Okay. This was the work done by Isaac Newton. This ended at the year, started with 1672 and ended at 1678. Okay. Students, remember one thing. Remember one thing is this. When this Newton did this work, no. So he actually took the Descartes theory. Descartes was the scientist. Descartes theory of the corpuscular model of light. He took that and did some modification in that. Did some what? Did some modification in that. He modified the theory and named it as optics, like this. Okay. And then in 1678, this ending year, 1678, he left the work on this. Then appears the new scientist whose name is Christian. He's a Dutch physicist. He's a Dutch physicist or scientist. His name was Christian Huygens. It's been pronounced as Huygens. Okay. So he's Christian Huygens. As you can see on the screen here. Am I on spotlight or what? Okay, it's fine. So his name was Christian Huygens. Okay. And he has developed the best of the theory of the waves. Okay. I mean, he told like this, by treating light as a wave, he was able to explain this thing. That is, he has given the wave theory of light. So till now, we were studying the corpuscular theories of light. That is, light has been treated as like particles of energy. Okay. But now you will be seeing that the wave it's what? It's a wave. I will see the wave theory of light. So in 1678, see, I will write all the names. Okay, don't worry. Descartes in 1637, 1672. This person was a famous father of what? Classical mechanics, Isaac Newton. And then comes wave theory of light by Dutch physicist Christians. What was that? Huygens. Okay. Then comes in 1801. So after these many years, one more physicist appeared. Who was this? His name was Thomas Young. And he has given a very fine, precise experiment as per assuming the wave theory of light. By considering wave theory of light, he has given a very good experiment. Okay. And that was interference experiment. Now, you people may be worrying that what is this interference experiment? We'll understand it. Okay, have patience. So we'll talk about interference also. We'll talk about diffraction also. And the last thing, we'll talk about what? We'll talk about polarization also. Okay. So have patience. As we are progressing step by step, we'll see all these topics again and again. Okay. So is the history cleared? Reply in the chat box, yes or no. Students, is the history clear? Reply in the chat box. I'm waiting. Okay, let us start it. Now the next thing. See, now we'll see the failures of Newton's corpuscular theory. What were the failures? Because see, if some other theory is to be implemented, like, it's been taken under consideration, that can only happen when the previous theories are rejected. So there must be some drawbacks or the failures of the previous theories due to which they been rejected. Okay, so these are the failures here. So what are the failures? The first is this. So Newton assumed that the light travels. What he assumed? That the light travels faster in the denser medium than in the rarer medium, which has been proved wrong. How we can say? Because we have studied this thing in the process of refraction, that suppose this is a boundary here. This is what a boundary, and this is normal to it. Okay. And suppose if a ray is passing, what happens? If a ray is passing like this, okay, it's incident. This is incident angle, and suppose this is a rarer medium. Somewhat it's having the refractive index as n1, and this is some denser medium, and somewhat it's having the refractive index as like n2. So when the light travels from this rarer medium to denser medium, it will bend towards the normal, and this is angle of refraction, where we'll say like this: angle of refraction will be less than the angle of incidence, or you can say angle of incidence is greater than the angle of refraction. And also we have proved this thing: the speed will be less in the denser medium. And geometrical optics previous classes, if you see this thing, you will get it, that the speed is less in the denser medium. I hope it's clear. You say what? We say the speed is less in the denser medium. Okay? Okay, students? But what Newton told this? Newton assumed this speed will be faster. So this is a very, it's against, it's anti, it's a contradiction. So next year's Newton told this thing, that corpuscular theory cannot explain the phenomenon of diffraction, interference, or polarization, which is again a failure. So these are two big failures of Newton. Please write this in your notes. I've removed the, in between it was creating a problem. I removed that thing. Please write in the notes, students. Write the failures and reply them in the chat box if you want me to proceed towards the next. Okay. Students, write all these things and reply in the chat box if you want me to proceed the next. Okay, let us see next now. Okay, let us see next. See, what is this geometrical? Let us recall the geometrical optics. Okay, so we have seen what? We have seen this thing. This was something known as electromagnetic spectrum. This is known as what? Electromagnetic spectrum. And see, if we see the leftmost thing, this is a light, a wavelet color light. It's a violet color light, and having the wavelength equals to 400 nanometers. Okay, and this is a red color light which is having the wavelength is equals to 700 nanometer. Okay, so if I name it, we know it's what? VIGYAN. Okay, so this falls in the visible region. This is what it falls in the visible region of electromagnetic spectrum. So if we connect the dots back, we can see like this, that we started with the ray optics or geometrical optics, in which we have taken the visible part of the light and we were treating light as paper pen representation, that like rays. Now we'll see it as like waves, okay, not rays. And also we have seen the corpuscular theory. Okay, so in this we were treating the wavelength of the visible light used, that it is very less, very less than the dimension of the objects in between. It may be plane mirror, this may be plane mirror, this may be spherical mirrors like concave or convex, this may be lenses like convex lens or concave lens, biconvex, equiconvex, concave. Okay, so from all these conclusions, at last we can conclude like this, that light can be assumed to be approximately traveled in straight lines. Okay, so this was the ultimate conclusion of the treatment of the light, or its interaction of the light with different of kind of object, mirror, lenses, and all these things. So we can conclude like this, that the light can be assumed to be approximately travel in straight line, can be assumed to approximately travel in straight lines. Okay, so geometrical optics covered. See, this is what? This is a candle. If you are going to observe this candle via a straight kind of object like this, it's sure, we know the rays are traveling in a straight direction. So rays are more compatible, like, it's like the chances, probability is more that it will come to the eyes. But if you're seeing with this kind of object, if there are no mirror connected on the side edges, it's very difficult that via other than reflection, the ray can enter into your eyes and you can see this candle. Okay. So next thing, what? Next is this. So this was all about geometrical optics. Now what we are going to understand in the wave optics here. In the wave optics, what the thing which we are going to understand is, so listen here. So here also we are taking the same visible region from the electromagnetic wave spectra. This is visible region. And in this, the point which we are going to take under consideration is this, that the size of the object and the path of the light is of the order of the wavelength of the light. Suppose, students, you are taking some say cardboard with a pinhole in this. Okay, so there is a cardboard and some slits are what? SLITS. What are these? These are gaps in the cardboard having the width in nanometers or millimeters. Okay, so this kind of thing will be there, and its dimension, they are saying the dimension must be approximately equal to the order of the wavelength of the light used, and that light must fall in what region? It must fall in visible region. Okay, I hope it's clear. So isme kya conclusion? The conclusion was this, that wave optics concluded this thing, that the light does not travel in straight line. Okay, it will not travel in straight line. And what geometrical optics concluded? It concluded that it will travel in straight line. So this is a contradiction, it's anti thing. Okay, so wave optics, we will say it is not supporting the geometrical optics conclusion. So the point which is concluded from the wave optics is not supporting that geometrical optics point, geometrical optics point. So these are both like anti-opposite. One says yes, one says no. Okay, it's like east-west. So now let us see. Now we'll dive into this wave optics again. Okay, more. See this picture on your screen. It explains you what. If you focus here carefully, this is the bending of light shown. When the light travels and some object is in the path of the light. I repeat it. When the light travels and some object is in the path of the light, so what happens? This happens कि light deviates from its initial path. So this is an experimental verification, experimental proof that light doesn't travel in straight line. Because if something is deviating from its initial path, it means you are not on a straight path. Okay, light does not travel in straight path. Okay, this is wave optics. It is all from the wave optics. So, but the geometric optics says it travels in a straight line. That's why we were considering these are rays. So remember, from now onwards, as we have entered into this region of wave optics, from now we'll not take those concepts. We'll take some of the concepts, but these concepts will drop. That will not say that the light travels now in what? In a straight line. We'll say it does not travel in a straight line. So from now, as the wave optics chapter has started, students, so we'll say what? We'll say light does not travel in the straight line. Remember this, write in your notes. Okay, so this was concluded in the wave optics. It's finished. This is the basic fundamental concept. This is the basic fundamental concept, okay, that light in the wave optics has been treated like this, that it doesn't travel in the straight line. Okay. Now let us dive into Huygens theory. See, it's pronounced as Huygens. Some it pronounced as Huygens. It's Huygens. He was Dutch physicist. So these are the objectives or contents, okay, of this Huygens principle. So first we'll go through that. What is this known as? Something as like wave fronts. What is this? Then we'll go through Huygens principle. That his theory, as per his theory, first he explained wave fronts. Then he has given a principle based on his theory. Then by using both of these things, above two things, we'll understand reflection and refraction. Yes, you have heard clearly, reflection and refraction according to Huygens theory. I mean, he will explain us what is happening actually when we treat light as a wave, how to explain this reflection and refraction process. Okay. Then at last, this is very interesting topic. And it's like, you know, I mean, you can feel this topic outside, like it's nearby us, like in the environment, we can see this thing. In the surroundings nearby, we can see this thing, the Doppler effect by the lights. Okay, you can even do this experiment in your homes. Okay, this is what Doppler effect. So at the end, we'll see this, but it will take time. We'll first start with this wave fronts and Huygens principle. Fine. So are you ready? We're having only 20 minutes. We'll just see for 15 minutes. At the end, I'll ask the doubts. If you're having doubts, you can reply. Otherwise, we'll end the class. Okay. Fine. So this is wavefront. I'm going to launch a video here. So see, observe this thing carefully. What is happening? The water drop. Hello, I'm audible. Okay, so this is Huygens principle. First, we'll go through the wavefronts. Huygens principle, reflection, refraction, Doppler effect. That's fine. Okay, reply in the chat box if you are ready with this, wavefronts. Okay, reply in the chat box. Students, reply in the chat box if you want me to launch this video. And reply there that the audibility is clear. Okay, I mean there are no issues, you know. Please reply it fast. Okay, so I am launching the video. Fine, I'm doing my work. So see here, students, what you can observe. We can observe this thing here, that these kind of circular tracks are being produced. Okay, and these are concentric circles, and they are increasing in radius. Okay, as this water drops drop by drop. Okay, like, so you can see the side view, the waves are being generated. Okay, so now if I talk about the wavefront, students, here, now if I talk about the wavefronts, let us see it. Definition now. Yes. So if you see, suppose you drop a ping pong ball in a pond, or a rock or a stone in a pond, okay, you will see circular kind of these vibrations are being set up. These are nothing but what? Wavefronts, okay? And the direction of the wave, or the energy as a wave which is traveling here in this, is actually shown by these perpendicular lines, which are always perpendicular to this circular vibrations or wavefronts. Okay, so this arrow are showing you what? It is showing you the direction of the wave traveling. Okay, and the circular locus, I mean, if you take all the points which are in same phase, if one is up, other is up. If one is down, other will be down. So it's not like this alternate, like plus minus. Okay, so if you take the locus of all those points, okay, and which are in the same phase, you'll get a circle. And here this is known as wavefront. Okay, so for different kind of sources, different shaped wavefronts are there. Now let us see the definition. So definition says like this: locus of the points which oscillate in same phase is called a wavefront. Okay, locus of the point which oscillates in the same phase is known as wavefronts. So suppose it's like epicenter. Okay, you know, earth there is an epicenter for that. Suppose vibrations are set up. Suppose this is a source of vibration. Circular kind of vibrations will be set up. Suppose from this center, its radius is R1. Iska center is R2. Iska center, suppose it's R3. So depending upon the radius R1, R2, R3, there are different kind of wavefronts here. Okay, and it says light rays. So I'm highlighting it. Light rays always travel in the perpendicular direction to the plane of the wavefront. Okay, so if someone asks from Yuki, like, tell me where, if I drop a stone, where the wave direction will be, or where the wave speed will be. Okay, so you will say the circular vibrations which have been set up, uske perpendicular will be what? The direction of the energy wave, or direction of the traveling wave. Okay, is it fine? So note it down. If you have noted it, like, reply in the chat box. Okay. Reply in the chat box, students. Okay. The speed with which the wavefront moves outward from the source is called the speed of the wave. Remember this point also. Okay. So you can see here, it's going like this. So we say what? The speed with which the wavefront moves outward from the source is called as the speed of the wave. Okay, I hope it's fine. So these all points are cleared. Now let us proceed. Yeah, what happened? Now let us proceed towards the next. Spherical wavefront. What is this? See, the circular wavefronts which we have seen were produced how? If we go towards the source, if we direct our attention towards the source, we can see like this. Those circular vibrations were set up like this. Suppose you have thrown a stone in the pond or like some water tank, you'll see the circular ripples there. Or suppose you like if you see the drop by drop falling of in that animation, there was what circular kind of vibrations there. So it all depends upon how the vibrations are being set up in a particular source. Okay, so if it's the cases are like dropping a stone or throwing a stone in a pond or a water tank, it will show you this kind of vibrations or wave fronts which we know now. But for spherical, we say if a point source, suppose suppose you make a room like dark, okay, and light some kind of like candle there, or you put a point source there, okay, so what's going to happen? The rays which will arise from it, if you connect all those rays, you will get a spherical wavefront. Okay, so it's written here, it says what? It says like this: if a point source emits waves uniformly in all directions, then the locus of the points which we have the same amplitude and vibration and the same phase are spheres. So it's like this. Let me show you. So watch this video carefully, it's very important. Okay, watch this video carefully, it's very important. So you can see what is happening in this. In this video, there is a source of light, and you can see a spherical wavefront, concentric spheres are being represented here. These are nothing but the wavefronts. And the direction of the wave is shown by these kind of curved arrows. Direction of the waves is shown by these kind of curved arrows. Direction is shown by these kind of curved arrows. Okay, understood? So this is what? This is spherical wavefront here. This is all about the spherical wavefront. I hope it's clear. So we say a small portion of the sphere can be considered as a plane. So suppose you now, if you want to understand for the plane wavefront, what is the plane wavefront is, na? We have seen circular, we have seen spherical. Now, what about plane? Suppose this on the spherical wavefront, if you take a rectangular, infinitesimally very small element ds, suppose it's rectangular shaped. Okay, so we'll call those as we'll call it as like what? Planar wavefronts. Okay, so now I'll be showing you the video. Please focus here. It's the next part. It will explain you how the plane wavefronts look like. Observe it carefully. Okay, so these were what? These are plane wavefronts. So how we can define them? We can define them like this. Small portion of the spheres can be considered as a plane. So these wavefronts are known as plane wavefronts, and it's shown here like this: 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. So now at last we'll talk about Huygens principle a little bit, then we'll end the class. That's fine. Okay. So what is Huygens principle? It says like this: suppose if we know the shape of the wavefront, I don't know what kind of shape it is. Maybe it is a circular kind of wavefront. Maybe it is spherical kind of wavefront. Maybe it is planar wavefront. We have seen all of these three types, but here we don't know which it is. Okay. So if we know the shape of the wavefront, suppose it's any of these threes, t equals to 0 at time 0, then Huygens principles allows us to what? Determine the shape of the wavefront in the future time, like at a later time, at time t equals to t. How it is? I'll show you somewhat. See, by treating each point on the wavefront acting as a fresh source of disturbance or a new vibration source. So see, suppose, hold on, suppose this is a source and these arrows are showing you what? The direction of the wave, direction of the energy wave traveling here. If this is a source, 3D source, it will be having spherical wavefronts associated with it, which I'm showing you by here. These are the spherical wavefronts. See, this is what this laptop is what? It's 2D. Okay, so we can't see the 3D things here actually, because this picture is also 2D plane, XY plane. So you're getting a circular kind of thing. Okay, but treat it to be like what? Sphere. So next, what happens? Now the Huygens principle says like this: if this locus of all these points, which is given to you, is like a sphere or spherical wavefront, if you mark all of the points here, students, if you mark all of the points here, these points will be acting as what? Like a source of fresh new vibrations. Okay, these are now the source of fresh new vibrations. And if you connect the peripheries of all these new vibrations, you will itself get, like, it will give what? The new location of the wavefront after time this. See, these are just symbols, don't get confused. You can use here t, so we'll get vt. Suppose we know this v equals to x by t, so x will be what? Vt. It means what? That the wavefront has traveled this much distance, that is equals to x equals to vt in a time t. And this black color kind of circle thing gives you the new location of the wavefront. This was the principle. Is this in clear, students? Reply in the chat box. So if I show you back, this was the second point. It says the new wavefront at any time later is obtained by taking the forward envelope. It means, what do you mean by envelope? By joining the periphery points of all the secondary wavelets. Secondary matlab, as you know, this was a wavefront. Iske all points were behaving like a fresh source of new vibrations. So the generated thing by them is what? Secondary wavelets. If you join them, this will give you the new location of this, hold on, of this wavefront after time t or tau. Okay, finish. So if this all things are cleared, we can end the class now. Simple. So remember, the conclusion is this: we started with ray optics. I mean, a little bit of the things, revision. Then we have seen wave optics. It's all of its points, and at last what? At last we have seen Huygens principle somewhat. Okay. So students, now I'm going to end the class. If you're having any doubts, can reply in the chat box, please. Please reply in the chat box. Please reply in the chat box if you're facing any doubts here. Okay. We'll meet in the next class. And if feedback you want to give in, you can or reply in the chat box, and then you can leave, students. Okay. Please reply and leave. Bye bye, everyone. So now I'm going to end the live stream here. Bye bye, everyone. Bye bye, all the YouTube students. Okay.